Okay, how's everybody doing? I hope everybody's well. I'm going to run through an example here where we're looking at this gamma distribution, which can be used in Bayesian statistics as a prior for a lot of different statistical models. And it's actually a really nice prior because a lot of times what you get when you start with a gamma distribution is something nice, either another gamma distribution or something that is relatively easy to integrate so you can calculate probabilities. So the gamma distribution has two parameters. Sometimes it's written alpha and lambda, sometimes alpha and beta. It doesn't really matter what letters you use. The first parameter is this alpha power on the x, and then the other one, the lambda or beta, is the constant in front of the negative x in the exponential part. And then the rest, the lambda, the alpha, and the gamma of alpha, that's just a constant essentially. It doesn't depend on the x. And so what these typically look like, these are usually right skewed distributions. So like a gamma distribution will usually be if you have your x and your y axis, then a gamma distribution typically will look something like this. Depending on the parameters, it will go up and then sort of tail off, and it'll have a very long right tail. All right, so and if the parameter alpha is just 1, then it'll be more like an exponential decay. In fact, an exponential distribution is just a gamma distribution. So these are two different superimposed examples of what gamma distributions might look like, poorly drawn. Okay, so part of the gamma distribution is this function here, which uses the Greek letter gamma, which is called the gamma function. And so try not to confuse these two things. There's the gamma distribution over here, and then the gamma function over here. They're actually different things. The gamma function is defined by this integral. What it is, it's actually the value of this number here that'll make the whole gamma distribution density function have an integral of just 1, so that the area under the curve is 1, so that it can actually be a probability distribution. The gamma function is interesting in its own right. It comes up a lot in mathematics. And so the first two optional exercises I gave you guys were just to work with the gamma function and just uncover some of its properties. The most important property of the gamma function is this one, that if you want to calculate gamma of a number plus 1, you just take the old gamma function of just that number and then you multiply it by that number. So it's like a kind of continuous version of a factorial function, actually. And so you can prove this first formula by integration by parts. You just write down the integration by parts formula. You calculate gamma of alpha plus 1 using the definition. And then you notice that the x to the alpha is easy to differentiate, so it would make a good u. And the e to the negative x is easy to integrate, so it would make a good dv. And you do the integration by parts, and it's pretty easy to get this expression that gamma of alpha plus 1 is just alpha times gamma of alpha. I'll let you work out the details on your own if you're interested. And then I point out that actually that immediately implies that gamma of n is just n minus 1 factorial. And you can prove that using induction. It's a good practice problem for induction. This is not a complete solution that I've written down here. It's just the two steps. You've got to prove the base case, and you prove the base case by basically doing the integral when n equals 1. All right. And so you would just go, and in this case n is the alpha, so you just put in 1 for, you put in 1 into this formula, so it's 1 minus 1 is 0, so x is 0, so you don't have an x, so you're just integrating e to the negative x. Not hard to do that. I'll let you work out the details again on your own. That's how you do the base case, and then you do the inductive step using the formula we just calculated in problem 1. Moving on, so this number 3 is the first one I definitely wanted you to try, and number 3 is just applying that property of the gamma distribution. If you know gamma for one number, then you know it for that number plus 1. So here's gamma of 1/2. It turns out it's the square root of pi. It's kind of a tricky integral to do that, but we're just going to take it as given. And then I ask you to calculate gamma of 3/2, which is 1/2 plus 1, and then gamma of 5/2, which is another 1 added to that. So gamma of 3/2 is just gamma of 1/2 times 1/2. And so it's just square root of pi times 1/2. There, we're done. And then gamma of 5/2, well, that's the same as gamma of 3/2 times 3/2, and we already found out what gamma of 3/2 was, so we just multiply that by 3/2, and we get this. Okay. If you want to check yourself, go ahead and calculate gamma of 7 halves, and it's not hard to do that. You'll see what you get. Okay, so the gamma function is a useful tool, but it's part of the gamma distribution, and that's really what I want to focus on today is this gamma distribution. And like I said before, the exponential distribution is a special case of the gamma distribution when the alpha parameter is just 1. Also, the chi-squared distribution is a special case of a gamma distribution. So we've seen chi-squared in statistics, and it came up when we were doing some of that multivariate normal distribution stuff, right? When you want to talk about the distance of an observation from the zero vector or the average outcome, that the square of the distance has this chi-squared distribution a lot of the time, and that's actually a gamma distribution, so it's another special case of gamma. So how do you use this in Bayesian statistics? Well, here's an example. Suppose you have a sample from a Poisson distribution with an unknown parameter lambda, and you want to choose a good prior. Well, a natural choice for a prior in this situation is actually a gamma distribution, and we'll see why when we do the calculation. So I just tell you in this problem to suppose you start with a gamma alpha beta as your prior distribution, and then go ahead and calculate the posterior distribution for that. So to do posterior, you take the prior times the likelihood function. Given our observation, the likelihood function, I went through this kind of fast in my solution. What you do is you just take you take the probability mass function for a Poisson distribution. So that's this function, what is it? It's lambda to the x and then e to the negative lambda. And so what you do is you take the different x's and you calculate that probability mass function for each one of these x's, and then you multiply them all together to get the joint probability mass function, because we're assuming here that these are independent observations. And then once you've multiplied them all together, you have this expression right here, and then you just reinterpret that and say, now that's our likelihood function, because now we're going to think of lambda as the variable and the x's as being fixed observations. And so that's the likelihood function. Then the prior density, I wrote it this way. I said it's proportional to this stuff, right? Actually, I'm using the gamma distribution, and the gamma distribution has some other crap in it. Let's take a look. So the gamma distribution is all of this stuff in this formula, and I'm ignoring the lambda to the alpha and the gamma function part. And the reason I'm ignoring those is because those are just constants. The only part that's a variable is the stuff that depends on x, and so I just need the x to the power part and the e to the negative lambda x part. And that's the part that I've written down. Because when I do my prior times my likelihood, all I'm going to get is something that's proportional to the posterior distribution, and so I don't care about any constants. I'll work out the proportionality constant later. So I take these two things, I multiply them together, and then my posterior distribution for lambda, given these observations, is directly proportional to this formula. And notice I've combined the lambda terms, so I had lambda to a bunch of x's added together, and then also lambda to the alpha minus 1, and just add the powers. And then I combine my e terms, and you again add the powers, and I also factored. And so there we go, that's it. That is the density function for the posterior distribution up to a constant, right? I don't know what the constant in front that would make the integral of this equal to 1 is. But actually, there's a trick here. I don't have to integrate this. I can just look at it and say, oh, well, this looks like a gamma distribution, right? It's an exponential with a negative lambda and a constant in front of that, and it's a lambda to a power. And conveniently, it's also got the minus 1. So this is our new gamma distribution. It has this as the first parameter, and it has this beta plus n as the second parameter. And so that's it. We're done. We know what the distribution is for the posterior. It's a gamma distribution with these two parameters. So that's really nice. If you start with a Poisson distribution, then you get, and then you use a gamma as your prior, then you get a gamma as your posterior. And it's really simple. You just take your observations, update your parameters, and you have a new, more precise distribution to tell you what's going on. Okay, next example is a little bit more complicated. It's a uniform distribution where we have an unknown parameter n this time. We've seen this example a couple of times already when we were doing likelihood functions. And now we're going to take a look at it from a Bayesian perspective. Instead of just doing the maximum or likelihood estimator for n or some kind of unbiased estimator for n, we're going to get a whole posterior distribution for n. So again, I'm starting with a gamma distribution as a prior distribution, and let's see what happens when I do that. So I write down the PDF, and then I turn that into a likelihood function by basically plugging in all my x's. And as long as all the x's are less than the n, then this won't change at all, really. And so I'll have 1 over n every time. I'll just multiply a whole bunch of 1 over n's together, and then my likelihood functions will be 1 over n to the nth power because I have n different observations. That's as long as all the xi's are less than n. If one of the xi's is too big, well, that can't happen, so the likelihood of that is 0. So I do have a piecewise function. There are 2 cases. That is important. I'll need that later. Okay, so there's my likelihood function, just the product of the individual PDFs. And then the prior is the gamma, right? And again, I'm writing the gamma distribution. Now this is a gamma distribution for n, so it's the n instead of the lambda that we had in the last problem. So n has a power of alpha minus 1, and then it's up here in the e with the negative beta. So there we go. That's the gamma distribution I'm starting with as my prior. And so then I do likelihood times prior is the posterior, or at least is directly proportional to the posterior. That's important. So the posterior distribution for n, given all these observations, is directly proportional to, well, I have a whole bunch of n reciprocals of n, and little n copies of the reciprocal of n. That's the same as saying big N to the negative n power, and so I put a negative n power in there. And then I basically am going to subtract, right, that away from the old alpha minus 1. And then the e to the negative beta stays the same, and that kind of looks like a gamma distribution. But there's a little bit of a twist here. It's not, because it's got 2 pieces, right? It's either this formula, as long as all your xi's were less than n, or put another way, as long as the n is bigger than all the xi's. But if the n is smaller than one of the xi's, well, that can't happen, so we can put a 0 there. We just know that we're not going to have the parameter n be smaller than any of our observed values. This was a random number generator. It was generating random numbers up to n, and so if the biggest random number was, whatever xi was that was the biggest, then we know n has to be bigger than that. Otherwise, we would never have generated that xi in the first place. So we can put 0 probability on n being smaller than one of the xi's. Okay, so that's a cutoff. And so like I showed before, gamma distributions sort of are these right-skewed kind of things. And so if I have my x and y axis, and now I've got this thing that kind of looks like a gamma distribution, but it's flat. It's got no probability mass until you get to a certain point, and then you've got sort of a jump up, a discontinuity, until you start using the rest of the gamma distribution curve. All right, so we don't quite have a distribution. We have that's gamma. We have this new distribution that's like a cutoff of a gamma distribution. And so we're not going to be able to use something like the built-in gamma distribution in R. We'll have to go and do these integrals ourselves for most of our calculations. Actually, there is a way to use R to do this, but it's a little more complicated. And for us, for right now, it's probably easier to just integrate this starting at the lowest possible value that n could be. And what is the lowest possible value that n could be? Think about that for just a second. Okay, so right, so if you've thought about it, the lowest possible value for n is whatever the biggest observation we got. We know n has to be at least that big, and it's probably more, right? So it's at least the maximum of all the xi's, and then it might be more than that. Okay, so that's what it is. This distribution is showing. So that's not a gamma distribution, but we've got the formula for it up to a constant. Now, how would you find out what the constant is that's in front of this? Well, you'd integrate this from 0 to infinity, find out what the area under the curve is. If the area is 1, great, then we're done. We don't need to put a constant in front of it, but probably it won't be 1. So whatever number we get, then we'll divide this formula by that number, and that'll then be a probability distribution. Okay, let me know if you have any questions about this, and I've posted a few homework problems where you use the gamma distribution 2, I believe, on the website, and I might post more on Monday. All right, hope everybody's having a good weekend. Talk to you later.